Hi, hello everyone. Today I am going to deliver a lecture on DC to DC converters. Last class we have discussed about AC to DC, and along with that we have discussed what are the different types of devices or power semiconductor devices are available, which are MOSFET, BJT, along with that IGBT and silicon control rectifier we have seen, and their operations also we have analyzed. Now, with the help of these power electronic semiconductor devices, we are going to utilize the different types of power converters, which are buck converter, and after that we are going to see buck converter, inductor, and capacitor design. Before going to the buck converter, what are the DC to DC converter and why we are using DC to DC converter? We'll see. First, coming to that DC to DC converter, it is nothing but it is a power electronic circuit which converts one level of DC voltage to another level of DC voltage. That is called DC to DC converter. That is the first point. Now coming to the second point, here the power converters are designed by using a switches or electronic switches we are going to use. Either it is MOSFET, transistor, or it may be a BJT. We will utilize based on the applied frequency or industrial application. We will use different types of power semiconductor devices. So now next coming to that, how DC to DC converters work. First one is when we are going to design a DC to DC converter, we have to utilize a switching technique. Which device we are going to use and what are the techniques are available, we have to analyze. First, let us take it as a when we are going to turn on the switch, the current will pass, and when it is turned off, the current will be blocked. Source current will be blocked. That is the thing that is called a switching technique. Now coming to that, here in DC to DC converter, we are going to utilize a inductor that will store the energy whichever it is supplying. Now next, the switch will be operated based on the pulse width modulation controllers. Here, when we are going to design any buck converter, boost or buck boost converter, we need to design separate PWM driver circuit that is called pulse width modulation circuit. As we know that PWM it is nothing but generation of 0 1 0 1 0 1 0 1 0 1 0 1 0 1. This is the way we are going to develop the pulses. That is called pulse width modulation. Now, whatever the output side capacitor we are going to use, we are going to smoothing the output current of or output voltage of the source, output voltage of the supply. We are going to smooth without any ripple. That is called we are going to make it as a output capacitor will be smoothing device. And these are the basic fundamental components are available in the DC to DC converter. Now, in the coming slide, we'll see how DC to DC converters are interfaced with the different types of renewable sources. Now, first, before going to that, what are the major advantages and if advantages are available when compared to the other devices? Here, modern switching converters will give highest efficiency. Like other devices, we will use these conversion DC to DC. It will give the power converter high efficiency. Now, basically transformers they will use for any voltage improvement or any other things. But here by using power electronic converters, we will give higher power density. That is the one major concern here. Now, next thing is power converters will be operated in battery powered any vehicles, battery powered vehicles or battery powered devices in order to supply the voltage. These are the three major concerns in the present scenario. It is available. Now, next, as I told you that DC to DC converters are playing a major role in different situations. Like first one is we are going to interface the DC to DC converter with different types of sources. First source is solar, second source is fuel cell, third source is battery. So these three sources we are integrating with the help of these DC to DC converters. Now these DC to DC converters, multi-input, single output boost converter circuit, we will use it here. And this is the concept I am explaining where DC to DC converters are actually used. This is the thing I am explaining here. First, foremost thing is solar. What is the drawback of the solar? Per unit cost of electricity generation will be very high. That is why we referring that solar PV cell must and should be utilized 100% by using the DC to DC converter. Now, second drawback of the fuel cell. Basically, there are many drawbacks are there. Here, fuel cell major drawback is it will deliver excess amount of currents when compared to the voltage. Suppose voltage will be 40 volts, the current will be, it will come in terms of 120 amps. That is the reason we have to interface with the DC to DC converter. Otherwise, the efficiency of the fuel cell will be below 20%. Now coming to the battery always it will give some moderate voltage that will be stepped up or stepped down by you based on the application necessity. Now based on the application necessity, this DC to DC converter it is supplies the power to the EV charging as well as next a ESS battery backups, and after that we are going to utilize the household applications. Now here everywhere if you observe that DC to DC power electronics converter is the major concern in order to maintain the voltage level across the each device. This is the major concern of the power electronic converters. That is why based on the application the power converters are divided into fundamental power converters are divided into buck converter, second one boost converter. Buck it is nothing but it is going to step down, it is nothing but buck converter. Boost converter it is nothing but step up. Next third one it is a buck boost combination of both, that is called buck boost converter. It will be used whenever the voltage requirement is very less, that time whenever the voltage requirement is high, both at a time it is possible with the help of this buck boost converter. So in this lecture, first we will focus on buck converter and how we are going to design the buck converter and what is the level of the voltage we will reduce by using the duty cycle. We will see. Now, first thing is what is buck converter? Circuit of the buck converter I will draw here. First one is circuit of the buck converter. Circuit of buck converter. Buck DC to DC circuit of the buck converter. Circuit of the buck converter it is nothing but it is having one voltage source, that is we are going to reduce the voltage, that is called, let us take it as a 100 volts VDC supply we will take, and we need to reduce the voltage 100 volts to different voltage levels that we will see. And after that I am going to utilize a MOSFET, that is metal oxide semiconductor field effect transistor. MOSFET I will utilize over here for reducing the voltage level of the source. Here what is the voltage source, why I am using MOSFET here? MOSFET it will give higher operating frequencies, that is first one. It will operate at different voltages levels, that is second one. And MOSFET high frequency application, along with that it will operate high power factor correction devices, that is also possible with that. So there are different types of applications are there, those are possible with the help of this metal oxide semiconductor field effect transistor. Now let us talk about the terminals of the MOSFET. This is the gate and this will be the drain and this will be the source. Drain, gate, source. Three terminals are there for the MOSFET. These things I have to indicate over here. Here, based on these terminals, we have to say that this is the N-channel MOSFET. What is that? N-channel MOSFET. N-channel MOSFET will provide highest efficiency and more power density. That is why we are referring. That is why we are referring that N-channel MOSFET. Now coming to the after MOSFET, what we have to take here? We have to take the diode, that is called diode D we have to take. Now after the diode we have to integrate with the source, that is why I indicated like this. And here this is the anode and this is the cathode, and along with that what is the voltage, we have to take it as a VD voltage we have to take it. So this is the diode configuration. After the diode we have to utilize a inductor in order to store the source energy, that is called inductor L0 I am going to utilize here. Next, after inductor, what is going to happen here? After inductor, what I will do? I will select the capacitor, that is called C0. This capacitor is used to stabilize the load voltages. And this is the voltage across the inductor, that is VL0. Voltage across the capacitor, that is VC0. We will take it over here. And after that, I am going to connect it a resistive load. This is the resistive load, that is R0. Now here under switch on condition what is going to happen we will see now. Under switch S is equal to on. Switch, that is nothing but MOSFET is on. What are the conditions are there? We'll see. Now, first condition is when the switch is on, diode D is going to be off. And after that, inductor L0 starts charging. That is the second condition. And third condition is capacitor C0, it is charging. That is condition 3. Condition 4, diode current ID, it is equal to 0. And fifth condition is capacitor voltage across the capacitor VC0, that is equal to V0. It will come here because there is no element in between those two. So these are the conditions which we can observe here. Now coming to the switch on condition, apply the Kirchhoff voltage law for loop 1. Loop 1, it is nothing but, let us assume that the operation of the circuit will start here. This is plus minus. This will call it as a source, and remaining all the passive elements will act as a sink. Now this case, whatever the current starts flowing from the source, that is, it will go towards to the switch. Then after that, this plus minus will apply here. Then that is the case, this device will be open circuited. Then after that, it will go to the inductor and it will go to the resistor and it will come back. This is the loop 1 we have to consider. Now coming to that, after that, so in this condition, if you observe that inductor and capacitor both are current sharing, and we can observe that this is loop 2. This is loop 2. Now under switch on condition, from loop 1 apply the Kirchhoff voltage law from loop 1. What is the voltage we will get it here? Minus times of VDC plus voltage is switched on, then that is the case, voltage short circuited. Then what is the voltage across the switch? That is 0. So here we have to take it as a 0 voltage plus VL0 charging VL0 plus V0 is equal to 0. This is the loop 1 we have to consider. Now coming to loop 1, what is the inductor voltage? VL0 is equal to VDC minus V0. So under switch on condition, this is the output voltage which we have observed. From this, what we can write it here, VL0, it is nothing but L0 into di0 by dt. These are the fundamental equations which we have to analyze, and we have to make it concept for the derivation of the output voltage gain. Now this is the output voltage V0. Now output voltage, when we are going to derive, so we have to consider switch on condition as well as switch off condition. Now consider the switch off condition. If you consider the switch off condition, let us assume that when the switch S is equal to off, what is the circuit condition? We will see now. Now this is the supply voltage. Let us take it as a VDC. We have considered that 100 volts. And after that, there will be a power electronic switch, that is MOSFET we have selected here. Let us take it as a 3 MOSFETs here. And this is the condition of the circuit. This is the gate, and this is the drain, and this is the source. So drain, gate, source, the 3 terminals we have considered here. And after that, under switch off condition, what will happen? We will see now. This is the diode, and after that, let us take it as a inductor, and after that there will be a capacitor. After that, there will be a resistor. All the terminals we have to indicate. Then I'll explain how it is going to operate under switch off condition. This is R0, this is C0, this is L0, this is the diode, and this is plus minus. Now coming to that, under switch off, first under switch on condition, what is happened here? This inductor, it is starts charging, that is called VL0, and this is also VR0. So under switch on condition, inductor, it is going to start charging. But coming to the switch off condition, let us talk about, this is the switch is going to off. When switch is off, what will happen here? Under switch off condition, whatever the inductor stored energy it is there, it will deliver towards the load and it will flows towards to the diode. So due to this short circuit condition, what will happen here? apply the Kirchhoff voltage law for loop 3. This is loop 3. And here there is no current, that is 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 equal to 0. So now this condition, under switch off condition, S is equal to off, current flowing through the switch Is is equal to 0, and current flowing through the diode Id is equal to IL, and current flowing through the load resistor, that is as usual we have to take it over here. And next, what is happening here, and whatever the voltage appeared across the diode Vd is equal to 0. Next, what is the load voltage? By applying Kirchhoff voltage law, apply the Kirchhoff voltage law for loop 3. If you apply the Kirchhoff voltage law for loop 3, then plus VL plus V naught is equal to 0. Then plus VL is equal to minus V naught. So this is the switch off condition. Then that is the case. What is the voltage here? VL is equal to minus V naught. When we are going to derive the output voltage gain, when we are going to derive the output voltage gain, we have to consider that VL voltage under switch on condition plus VL voltage under switch off condition, that is equal to 0. So this is the condition we have to consider for deriving the output voltage. Now, foremost thing is, we will see here VL is equal to, what is the switch on condition? Switch on condition, that is T on condition. VL minus, what is VL? It is nothing but Vs minus V naught. Then that is the case, that is T on plus minus V naught T off is equal to 0. This is the fundamental formula which we have to observe. Now, what is T on? T on, it is nothing but D times of Ts. As we know that duty cycle formula, duty D is equal to T on by Ts. This is the fundamental thing which we have to observe. Now, coming to this, if you people observe that T off is equal to 1 minus D times of Ts. These are the two fundamental things which we have to observe. From this, how we can write it here? Total average voltage appeared across the inductor is 0. Vs minus V naught. Here T on, it is nothing but D times of Ts. Next, plus minus V naught. What is T of here? T of it is nothing but multiplication of 1 minus D times of Ts. It is equal to 0. So these are the fundamental waveforms which we have observed over here. Now apply both the side multiplication. First we will take it as a Ts will be the common. Then Ts we will take it as a common. Then that is the case. Vs minus V naught. Then D minus V naught 1 minus D is equal to 0. Then finally, what is the formula will come here? If you observe that, what is the formula here? Vs D times of Vs minus V naught into D times minus V naught plus D times of V naught is equal to 0. This is the overall output formula for the buck converter circuit under operating switch on as well as switch off condition. So this will be going to get cancelled. Then that is the case. Finally, if you observe that Vs into D is equal minus V naught, that is equal to 0. Then V naught is equal to D times of Vs. Then what is the voltage gain? Finally, voltage gain, V voltage is equal to V naught by Vs is equal to D. This is the voltage gain of the buck converter circuit. Now we will see how this converter will act as a buck for different duty cycle. Now if you observe that, what is the output voltage formula here? V naught is equal to D times of Vs. Let us assume that Vs voltage here, next duty cycle here, next V naught is equal to D times of Vs. If you observe that, let us take it as 100 volts. After that, let us take it as 50. After that, it will be 20. After that, it will be 10. Otherwise, if you take it as a simple thing, if you take it as a duty cycle changes, what will happen? We will see now. Now, let us take it as a For 100 volts, for 100 volts input, let us take it as a 0.1 duty cycle, 0.2 duty cycle, 0.3 duty cycle, 0.4 duty cycle. What is the values we will see now. So here input voltage is constant, output voltage we are going to vary with respect to the duty cycle. Now what is the output voltage V naught? 100 into 0.1, how much? It will be 10. 100 into 0.2, how much? It will be, let us take it as a, when duty cycle changes, what will happen? 0.1, it will be 0.1 into 10, 100. 0.2 into 100, it is nothing but 20. 0.3, it is nothing but, it will be, take it as a, let us assume that 0.3 into 100, it is nothing but 30. 0.4, it is nothing but 100, it is nothing but 40. So here, whatever may be the condition, what is happening here? Input voltage is 100, but output voltage is less than 100 volts. So that is the condition which we can observe here. So input voltage, what is the input voltage? That is VDC, 100 volts, but output voltage at different duty cycle, it is less than 100 volts. Those from this, what we can observation have here, observation. We have to note down few observations here. First observation is input voltage is constant. Input voltage is constant. Input voltage is constant, but output voltage is, but output voltage is, but output voltage is varying in varying in step down form. Step down means reduction form. Now, second point is when varying the duty cycle, when varying when otherwise when vary the duty cycle, when vary the duty cycle in increasing manner, in increasing fashion, then the corresponding output voltage also, the corresponding then the corresponding output voltage is increased, then the corresponding output voltage is increased. So these two things we have to observe in this buck boost converter circuit. Now for the derivation of the inductor as well as capacitor, we have to consider that how the waveforms will come for the different configuration we will observe. Now we will go for the waveforms configuration. First foremost thing is boost converter waveform. Let us draw here again fundamental circuit so that the waveform understanding will be very clear. This is a DC circuit, as we mentioned that. This is the MOSFET circuit. Sorry, MOSFET arrows will be different. Here, this is the MOSFET circuit. We will make it as a simple manner. This is the MOSFET circuit, and this is the gate. And from this, we are going to take it as a diode that is over here. And after that, we will draw this plus minus. This is VDC, and this is diode. Let us take it as a, this is anode, this is cathode. And after that, let us take it as an inductor as well as next capacitor as well as next resistor. We will take it here. This is the R naught, this is C naught, this is L naught. This is the basic buck converter circuit. This is the switch, and this is the load voltage. So this is the overall thing, and the current flowing across this is I naught, and across this one is V naught. We will take it here. That is called VR naught. We will take it here. This is the buck circuit, buck converter, buck DC to DC circuit. So this is the buck converter circuit. Now we will see the waveforms, how the waveforms will come step by step. We will observe here. But coming to the waveform, we will draw a one vertical line for drawing the all the waveforms, how it will come for different operations. How it will come for different operation. First, foremost thing is, let us take it as a, this is the vertical line. we are going to observe here, then that is the case. First take it as a, this is the vertical line. From this we will take it as a circuit over here. Sorry, we have to take it as a line here. Let us take it as a horizontal line. Let us take it as a horizontal line. Sorry. Again, okay. Let us take it as a horizontal line. This is 0. And here we will divide the line into different parts. When it is going to switch on, when it is going to switch off, we will see here. First thing is, this is the condition when we are going to see this. And after that, this is the condition, we will see this one. And after that, this is the condition we can see here. And after that, this is the condition we will see here. So these are the conditions which are more than enough. This is switch on condition. This is switch off condition. This is switch on condition. This is switch off condition. This is switch on condition. This is switch off condition. Like this way, we are going to design the circuit. Now, before going to that, this is the switch on condition. Now, this is the switch on condition. Now, this is the switch on condition we have to observe. So, this is the way we have to derive. Now, we will observe what is the output voltage and how we are going to derive it. First, foremost thing is we will take this circuit. This is the first circuit. Let us take it as a T in terms of seconds. This is also take it as a T in terms of seconds. Let us take it as a, this is 0. And again, this will be take it as a T in terms of seconds. And this is also another waveform we have to take it. This is, let us take it as a, this is, let us take it as a, this is, what is that? This is V naught. This is IS source current. This is diode current, source current, diode current, output voltage, and next one is output current. Next one is we have to take it as a diode voltage. Let us take it as a VD. This is 0. Now one by one waveform we are going to draw how it is going to vary with respect to time. We will see now. Now first foremost thing is let us talk about the waveform. When the switch is on, what is happening here? There is a current flowing through the load. There is a current flowing through the load. Then that is the case. The voltage will come to this level. In this case, what is happening here? Whatever the inductor current it is there, let us take it as a, instead of diode I naught current, we will take it as a inductor current so that we can understand the things very easily. So first we will take it as a, this is the inductor current. Under these circumstances, what is the inductor current? It will start charging and it will go towards to this. Next, when the switch is on, diode current is 0. That is why I am representing here 0 current. Now source current, it is nothing but exactly inductor current. That is why I am indicating here. Now diode voltage, under this condition open circuited means there is no voltage. That is why it is 0. Now what I am going to represent here under switch off condition. Here this is the switch on. Now this is switch off condition. Under switch off condition, what is happening here? Whatever the switch current it is there, it will slowly comes towards to the inductor current. It will discharge. It will get discharged. And along with that, what is here? Is is equal to IL. So automatically this will also, sorry, this time so source current is 0, right? We have to clearly observe that source current it is not there. Under switch is off, there is no current flowing through it. And that is the case. We have to indicate it is 0. So here 0 current. And along with that, here what is there? Diode current is there. Then that is the case. Diode current as it is nothing but here ID, it is nothing but IL. Here it is nothing but IL, it is nothing but IS. So these two equations we have to remember when we are going to derive the inductor value and capacitor value. This is switch on condition, which we have to take it as a dotted line. Let us take it as a switch off line. Then this will be take it as a switch off condition. So this is the switch is on. This is switch is off. So now again switch is on. What will happen? Switch is on. Source current will be there. That is equal to the inductor current as it is. We have to take. And after that it will be 0. Again it will be the source current will be there. Then that is the case. We have to indicate like this. This is the uh, source current. And coming to that, under switch on condition, what will happen? So this current will be 0, diode will be open circuited. So here diode will be open circuited, here diode will be short circuited, here diode will be open circuited, and again same thing, it will get discharged to the diode, that is short circuited. Here we have to represent. Now coming to that, again inductor starts charging, it will goes towards to this, then that is the case. This is charging period and this is discharging period. We have to observe this. And next again, whatever the load current, whenever switch is on or off, the load current will be constant. That is why we have to represent that I naught current. So here what are the things we have observed? Under switch on condition, IL is equal to IS. Under switch off condition, ID is equal to IL. So these are the formulas we have to observe. Under switch here, if you clearly observe that there is no voltage under switch off condition, under switch on condition only there is a voltage because there is a short circuit path across the load. So this is the switch on condition, then there will be output voltage. Otherwise, there is no output voltage. So this is the basic fundamental waveforms which we have to observe. And next class, I am going to explain the how we are going to select the inductor. That is inductor L. We are going to select how we are going to select inductor as well as capacitor. Next class, we will see how in detail we will see the all the parameters. Thank you so much. Thank you all for watching my my lecture. Have a nice day.